2.5 is the last general derivative rule that we're going to encounter, and it's called the chain rule. And what the chain rule does is the chain rule talks about how to handle a function that is a composite function. Now, you encountered composite functions back in algebra at some point, probably in high school for the very first time. All a composite function is what looks like a function inside of another function. So maybe you have a square root with stuff inside of it, or maybe you have something with a power on it with stuff inside of it. And so you've got something that looks like it's inside of something else. That's what a composite function is. And what this derivative rule says is that I take the derivative of the outside function, whatever's going on outside, and I leave the inside part written without change. So a lot of times I will say we want the derivative of stuff, right? The stuff doesn't change. It's just the same stuff it was before. So this piece right here has the g of x written exactly like it was originally. No change made to that part. But then we actually take a look at what happens because of that g of x function, because obviously it plays a role in the derivative. And we actually take the derivative of that piece as a multiplication factor afterwards. That's the chain rule. And it's easier to see it happen, I think, even than to describe what's happening. So I want to just show you an example and you can see how it works. You ready to try one? Okay. So on this particular one, it looks like we have, in fact, often you will see parentheses written when you're working with these kinds of functions too. It looks like I have some stuff in here that I'm circling around in red. And that stuff inside in red, we're going to be our inside function. And then there's stuff that's happening to it on the outside of that. So on the outside of it, just looking at the outside, I've got a 2 in front. We know how to handle that. And I've got a power of 5. So if I took this stuff and I raised it to a power of 5 with a 2 in front, what would the derivative of the fact, what would I do with this 5? We would bring it down, okay? And I would multiply it by the 2, right, when I bring it down? So I've got the 2 that's there originally, that's the constant multiplier rule, multiplied by the 5 that's the exponent, so I've got a 10 now. And then I would take the exponent of 5 and I would make it a 4. This right here is the derivative of the outside. The kicker is that the stuff inside the parentheses doesn't change. So whatever it was to start with, it still is that. That's the derivative of the outside with the inside unchanged. But to this, I actually need to multiply the derivative of the inside. So now I take a look at the 6 minus x squared part, and I say, what's the derivative of 6 minus x squared? Negative 2x. And that right there is all of the calculus involved in the problem. That's where you would leave the problem if you're doing the quiz next Monday. There's really only one small step to do right now anyway to simplify it. What can be combined? What can be simplified? The 10 can't be distributed, actually. Why can't the 10 be distributed? Because we got a power of 4. If I didn't have the power of 4, we could distribute the 10. But the 10 can be combined with something else. The 2x at the end. Yeah, so I can combine these two together. It's not actually a distribution property, it's a commutative property. I'm just sort of changing the order of things because it's all just pieces that are multiplied. So I can take the piece at the end that's multiplied and multiply by the piece at the beginning. The order doesn't matter. So that's a commutative or associative kind of property as well. So this is negative 20x. And then I have the 6 minus x squared to the power of 4. Now, I'm not going to do this because it would take quite a long time to do it. But there is another way to do this problem if you didn't have the chain rule. Any idea what you could do?
Like multiply out the inside, the part in the parentheses so that it would work with the power rule?
Yeah, you could. Because this is just a power of 5. I mean, I've basically got that, what was it, 6 minus x squared times 6 minus x squared 5 times. So if we wanted to, if we were so inclined, we could multiply that 5 times, right? And then we could use the power rule. I don't think we want to do that. If it were power 2, fabulous. If it's power 5, not so friendly. don't want to do that 5 times. But there actually is another way to do this particular problem. It won't look quite the same as this one at the end because this one's still in factored form at the end. And the other way, it would actually be all in, in distributed out form instead of being in factored form. But the answer would be equivalent. It just would be in a different form. So this is really friendly to avoid us having to do exactly what Grace suggested we actually could do, because I don't want to do that multiplying by 5 out times, multiplying it out 5 times, right? Yeah. All right, take a look at this one. First of all, as you take a look at this one, what does it look like you've got going on here? It looks like a quotient rule. And you could use the quotient rule to do it. It'd be okay. But the quotient rule is actually not the friendliest way to do the problem. And it's also sort of weird. The reason it would be a little bit weird is because what's the derivative of the numerator? 0. And so usually when we use the quotient rule, we're dealing with derivatives that don't become 0. It's a little bit awkward to work with in that way. It could be done. You'd get the right answer. It just is a little awkward. All right? So instead of dealing with it as a quotient rule, I'd like to show you how to deal with it as a chain rule. We could actually write this like this. Right? Yeah, you just take everything from the denominator, pull it up, all together, grouped all together. You can't sort of just pull up pieces of it and make them all negative exponents. That's not possible. But you can keep all of it together and move it up and make it a negative exponent. Does it look like a chain rule now? It looks an awful lot like the last one we did, actually, doesn't it? So we can actually operate with it in the same way. So what is my outside function? Yeah, that exponent with a -1, yeah? So what's going to happen to the -1? It's going to be a multiplier, yeah? So I'm going to have a -1 here. And what will the -1, yeah, you're already there. The -1 become a -2. What's going to go inside the parentheses? The same thing that was already there. So I've got x squared plus 3x and -1. Then what do I need to do? Derivative of the inside. So what's the derivative of x squared plus 3x minus 1? Perfect. Now this one actually simplifies again, and it simplifies pretty quickly. I can combine that 2x plus 3 that's at the end with the -1 at the front, just like I did in the last problem. The other thing that I can do is, since this is all written with a -2 exponent, I can actually take it and move it back down on the bottom. So the first thing I'm going to do is actually show that part of it. This is x squared plus 3x minus 1 on the bottom. And that kind of makes sense, because if we'd done the quotient rule like Zach said he saw at the beginning, which of course we could have done, we would have gotten the denominator squared. And that's what we've got here, right? Denominator squared. So that actually happened. And then I can distribute that -1 to the 2x plus 3. So I have -2x minus 3.
So you can distribute the -1 to the x squared plus 3.
You couldn't. Why?
Because
Because it
it has power.
has power. Yeah, that's exactly why. What you want to remember is that order of operations say that exponents happen before multiplication. So if you try to do something in between with a multiplication before you've actually squared something, you've disrupted the order of operations. You've done things out of order. Yeah. Okay, is this one all right? So recognizing again that if you wanted to do the quotient rule on this one, you could have. It didn't actually say we had to use the chain rule, and you would have gotten the same answer. And it really wouldn't have been that many different steps or anything like that. It just would have been a little bit different process. Alrighty, now it gets fun. This one is very different than what we've done before. First thing to recognize, however, is that square roots, which we have dealt with before, can be written as powers, right? So we can actually start this, and there's more than one way to do this particular problem. I'm going to show you one option, and then we can just kind of talk about what other things you could have tried. So we can write this as a power 1/2. There it is. All right, so we have stuff inside of a parenthesis with an exponent. That's not any different than we've had so far, right? Stuff with an exponent, you guys know how to handle that because you've done it several times now. So somebody tell me what the outside derivative is going to be. Right. So this is the outside. And then inside goes the same thing. All right, everybody good so far? I don't want to say the problem comes in, but the more difficult part here now comes in with the fact that what's inside that parenthesis is actually a quotient. So when I do the derivative of what's inside now, I actually have to use the quotient rule. So I'm using the quotient rule in the middle of using the chain rule, right? See, these build on each other. All right, so we're going to attempt to do that piece then. All right, so the quotient rule in the middle of doing the chain rule. So the quotient rule says I take the denominator, so 2t plus 3, and I multiply it by what? Derivative of top, which is 6t. Yep, you guys are already telling me, good. Minus the numerator, which is the 3t squared minus 2, times the derivative of the denominator, which is 2. All of this is written over the bottom square, 2t plus 3 quantity squared. If you were working on the quiz next Monday, you could stop. You guys are going to just be hoping we do more quizzes, I can tell already. This one actually has quite a bit of simplifying that we're going to do, though. We actually have to do quite a bit to make this actually consolidate down into the smallest form. So the first thing to do is to simplify that quotient rule. That's not too bad. So we've actually got the 1/2 still here. I've got the 3t. In fact, you know what? Let me just rewrite a couple pieces of what's going on in this parenthesis. The fact that this is a negative exponent, it can be turned into a positive exponent. How? What can we do with this? We can flip it. So we can actually do the reciprocal here, and we can make the exponent positive. Do you guys remember that? Okay. The other thing that I could do, and I will need to do it later anyway, so I'm going to do it now at this step, is I'm going to write each of these pieces, the numerator and the denominator, separately with a power of 1/2. So I'm actually going to write the new numerator, which was the previous denominator, 2t plus 3 to the power of 1/2. It's on top now because it was on bottom before. And then the 3t squared minus 2 is now on bottom with a power of 1/2.
So if you said the is changed, that negative?
Yes, when you flip a fraction upside down, it actually changes the sign on an exponent. Okay, so that's this piece. Let's simplify what's going on here, though. So we're going to distribute some pieces and combine some pieces, and let's see what we get. The first thing to recognize is the denominator stays the same. This is 2t plus 3 cubed. All right, so I have 6t times 2t plus 3, which gives me 12t squared plus 18t. It almost sounded like AT&T. Oh, it shouldn't be, because I was careless when I was writing it. Thank you, Jalissa. It's squared, thank you. All right, and then the second piece here in the numerator is I've got this negative to distribute and this 2 to distribute. So I'm going to get negative 6t squared and positive 4. Are we good with that? Okay. I know that numerator simplifies, but I also have something else that simplifies. What else simplifies? Do you see it? Where are you seeing?
I was just thinking
Yeah. This one, right, Brooks? Yeah. These match, don't they? They have different exponents, but what's being operated on, powers or whatever, the 2t minus 3 or plus 3 matches. So this is equivalent to having one half of these on top and 2 of them on bottom. And we have a property that says that we can actually either subtract exponents or move things around. If I actually move this one back down to the denominator, it would have a negative 1/2 power, right? And that negative 1/2 combined with a 2 would give me 3/2 or 1.5, right? So let me do a step where I actually show that so you can see it, because I can see a couple of you just sort of zoning out as I talked. But let's go ahead and simplify the numerator of the second fraction. So what is 12t, what does this simplify to, this piece right here?
6t squared plus 18t.
piece. Is everybody good with that piece? I'm going to take the part that's squared in red in here, and I'm going to put it in the denominator. So I'm going to have the original first denominator, which was this 3t squared minus 2 to the 1/2. I'm going to bring the 2t plus 3 to the 1/2 down as a negative 1/2. And then I have the 2t plus 3 squared down here. And so then since I have the two quantities that match, I can add their exponents to give me that positive 3/2. Sorry, just buying myself a little bit more space here. So these two can combine and become what with an exponent? 3/2. Do you guys see that okay? There's one other thing I can do. Do you see it? One and I'm done. I'll give you a hint. It has to do with that number right there. Mm-hmm. Okay, say that a little bit louder, Jamie.
Simplified from the top.
Yeah, that 2 that's there can be simplified with the numbers up here because they all happen to be even. It wouldn't have had to be even. They just happen to be in this particular problem. So we can actually simplify those pieces as well. So this 1/2 will reduce, I would actually get 3t squared plus 9t plus 2 on top. And then on bottom I have 3t squared minus 2 to the 1/2. And I have the 2t plus 3, and then to the 3/2. So who's excited you don't have to simplify anything on Monday? That one required a lot of simplification. No argument, right? Yeah, it did. All right, I think we've got more. We do. All right, what are the directions saying we're going to do differently on this problem? Second derivative. So we know how to find the first derivative, and we've talked about a couple of different occasions about second derivatives. And this one actually is going to be using the chain rule to find the first derivative. So how can I rewrite this function right now to be able to use the chain rule well? Right. All right, so let's take the chain rule to find the first derivative first. What do I get? 1/2. X squared plus 4, good. To the negative 1/2. Very good, times 2x. You guys are getting the hang of this very well. We could keep going and just go straight into the second derivative here, but we also could simplify if there's ability to do so. And there's a little simplifying because I can reduce this 2 and this 2. And then I'm just going to write the x at the beginning, not because it really matters, but it's just a little bit more common to see it written that way. So this is the first derivative. Oops, that's a negative exponent. This is the first derivative. And then I need to find the second derivative. Now, if I were working with this particular problem and I were just asked to find the first derivative, I wouldn't leave it written this way. I would go ahead and move that negative exponent back down to the denominator. And since it started out as a square root, my answer would include it as a square root. Okay? Now, but we're not asked to actually stop the problem here, so I don't have to do that on this particular step. I can just keep going, because this is the form I really wanted in order to do the second derivative anyway. Does that make sense with everyone okay? All right. Now, the second derivative has an interesting feature, and this is the first one of these we've encountered. What am I going to have to use to do the second derivative? A chain rule and something else. I'm going to also have to use a product rule. Do you guys see a product here? I have two separate functions that are being multiplied. I have the function x, and I have the function over here that is the x squared plus 4 to the negative 1/2. This is a product rule. inside of my product rule is a chain rule. That is, in the second piece over here, I've got a chain rule going on. But overarching, this is actually a product rule now that I'm going to be working with. So we haven't done a product rule today. We did it last time. What do I have to do if I'm finding the product rule? The first function rewritten, and then the derivative of the second one. Okay, so what's the derivative of the second one? Well, that's where the chain rule comes in that Brooks mentioned, right? So I need the chain rule to take the derivative of the second function. So that negative 1/2 comes down just like it did before. And then what? Not yet. X squared plus 4. It's a chain rule in the middle of it, right? To the negative 3/2 times the 2x that's inside the derivative. So this whole piece, all of this underlined in green, is the derivative of the piece right above it that's underlined in green. Be happy that the next piece is easier, but yes, Micaiah?
I'm confused as to where the 2x came from.
The 2x at the end came from the derivative of the x squared plus 4 on the inside.
Oh.
There's a lot going on when we combine two rules together, right? We did the example here before. We did an example of a quotient rule combined with a product, or quotient rule combined with a chain rule. This one's a product rule combined with a chain rule, right? So the overarching rule really is the product rule, but inside of doing the product rule, I also have to do the chain rule. I'm not done because the chain or the product rule says then I have to do an addition sign, and I have to do the second function rewritten right here, and the derivative of the first function rewritten right here, in whichever order you'd like. I'll do the derivative of the first function first. What's the derivative of the first function? 1. And then the rewriting of the second function looks like that. That's actually the derivative. So let's say, for instance, on Monday, you actually were given this function right here that we've called y prime up here. That's something you could be given on Monday. And if you started out right here and you needed the derivative, this is what you would get, and you would stop. We're not going to stop right now. We're going to simplify that. The x's here, or the 2's here, are going to simplify. I've got a negative, and I've got x and x. So this is actually negative x squared on top. I'm going to put this piece down in the denominator because it's a negative exponent. So this is x squared plus 4 to the 3/2 in the denominator. To this, I'm going to add the 1 over x squared plus 4 to the 1/2.
Why is it x squared?
Why is this piece x squared? Because there's an x here and here.
Oh, okay.
Yep. There's something else I'm going to have to do. Any guesses as to what it would be?
I'm getting my turn at the bottom.
We're going to common denominator. We're going to combine those fractions. It's not as bad as it sounds. They actually are very similar already, the two denominators, right? It's just that the first one is actually got a power of 1.5, and the second one has a power of 1/2.
So you just multiply the second one by the second.
You got it. Yep, you just multiply the second one by the x squared plus 4. Top and bottom. Because that's the power of 1 that we're missing, so to speak, when we think of the 3/2 as 1.5. Should give myself more space here. No, I didn't. Okay. Let me do this. That's not what I want to do. All right, let me go right here. So what ends up happening on the top then is that I have a negative 1/2 here. I'm sorry, negative 1/2. A negative x squared here. And I have a positive x squared here. So those add to 0. So the numerator actually just becomes the number 4. And then the denominators now match, and that is my new denominator then. X squared plus 4 to the 3/2. And that is the second derivative, actually, that we just found. Any questions on that one? Yes, Grace?
Where'd you get the 2x in your first
right here. It's the derivative of x squared plus 4.
Okay.
It's the inside derivative. Yep. So remember when you're doing the chain rule, you take this piece down, you rewrite the piece in the middle, and you raise it to the new power. And then you look inside and take the derivative of what was inside of that function that was rewritten. So that's the 2x.
Which part is the chain rule and which part is the product?
The whole thing is the product rule. This piece plus this piece are the product rule. The chain rule part happened when we underlined in green. What you see underlined in green is the chain rule. Okay? There's one more example, and it's not a very difficult one. This is one you're going to do an example of this in your homework. It wants you to compute a derivative for h of x equals f of g of x. They want you to find h prime of 1, and then they give you a bunch of numbers. There's no functions here, like as in an equation for you to have to work on anything. But you actually have to use what it means to actually have a derivative of a chain rule. So this is h of x. It equals f of g of x. So by definition, what is h prime of x? What does that look like?
The chain
Yes, like what does it say?
F prime
Mm-hmm.
times G
Right?
times G prime.
Right. So this is the chain rule. I'm supposed to be finding this function at x equal 1. So we're going to find this at x equal 1. Remember, all these parentheses have nothing to do with multiplication. They're just holding functions inside of other functions. So I'm not doing g times 1 here, right? I'm actually doing the function g of 1. Now, parts of this I know. What is g of 1?
2.
It's 2, right up here. So I can replace the g of 1 with the g of 1's value, which is 2. So this piece is up here. So I can replace this with the number 2. The f prime stays the same on the outside. I didn't do anything with it yet. What is g prime of 1? That's the negative 2 over here. Do not be tempted to multiply the negative 2 and the 2 here. This 2 that's in red is inside of a function called f, okay, or actually called f prime. But I know that value. What is f prime of 2? Oops. So f prime of 2, we said up here is 3. So this piece right here is actually the number 3 times the second piece over here, which was the number negative 2. And what does that work out to be? Negative 6. So h prime of 1 is negative 6. There's no functions. There's no actually working through an algebraic problem on this one. But there is the reasoning involved. Because if you'll notice back there in the directions, they give you the function and the derivative at every single possible point you could need. So you've got to figure out which one you're supposed to be using in which place. It's done that way on purpose.